Now, the last pathway, the oxidative phosphorylated pathway. This pathway has the biggest capacity to make the most ATP, is very slow. So if you look at the hierarchy of phosphocreatine, very fast, low capacity, glycolytic pathway, the anaerobic is slower than the phosphocreatine, has a bigger capacity, produces a little bit more ATP, but it doesn't produce as much ATP as the oxidative phosphorylative pathway.
This one needs oxygen.
This one needs oxygen. And it happens in the mitochondria, or the mitochondria as plural. So with this has two parts actually. The oxidative phosphorylated pathway actually has two pathways in it. There's the Krebs cycle, and named after Hans Krebs, who discovered it, and he got a Nobel Prize for it, and he apologizes for everybody out there. And then the second part of it is the electron transport chain, which is probably makes no sense whatsoever as far as the name goes. If you think of it as the ATP synthesis pathway, because that's where the vast majority of ATP in your body is being made. And so think of it as that ATP synthesis. That pathway is the ATP synthesis pathway in your body. And just for the exam, electron transport chain. But for you to have some sort of relationship with what the hell this means, that I would go with ATP synthesis pathway. And so the Krebs cycle, what the take home is for the Krebs cycle is, it's a bunch of reactions you don't need to remember, but because there's more reactions, it's slower. You get some ATP, very little, and you get NADH that we talked about in the previous video, which is basically something that just holds hydrogens. And you have another protein called another carrier called FADH2, which also carries hydrogens. So basically they're hydrogen carriers, and which is important for the last step, which is the ATP synthesis, aka electron transport chain.
So you said this is the slowest way of producing ATP. Would you say it's part of the reason is because there's so much going on? It just takes a lot of time.
And there's the more pathways, the more enzymes are involved, the slower processes tend to be. And so at this point, you're still not getting a heck of a lot of ATP. Well, where's all the ATP? All the ATP comes from these two carriers that nobody really thinks about. NADH, nobody's like, I need more NADH. But NADH and FADH2 are made from niacin and from riboflavin, so your vitamin Bs. So this is why you need vitamin B, niacin and riboflavin for if you're not doing very well energetically, you're not having enough of that. But what happens is these move into the ATP synthesis pathway, and the ATP synthesis, aka really what we're calling it is electron transport chain, happens in the mitochondria. It's very abstract. What I find is the easiest way to think of it is like a hydroelectric dam. So when you have water, right? So you have water in a waterfall, and as it falls, it passes by a turbine, right? And it turns the turbine, and then that turning of the turbine then can be used to make energy. And the electron transport chain ATP synthesis pathway is very, very similar to that, but it uses hydrogens. So the hydrogens, and also electrons, which is why it's called electron transport chain, but the hydrogens are used to make so the hydrogens basically are falling off the waterfall, but instead of it being a distance in gravity, it's a difference in concentration between the hydrogens outside of the inner membrane and inside the inner membrane. So hydrogens basically rush past an enzyme called ATP synthase. And that ATP synthase can then make ATP. And then the hydrogens go into the mitochondrion, and what's inside the mitochondrion is oxygen. So as the hydrogens come in, they then they bind to the oxygen and become water. So then this gradient can continue. And then you get a ton of ATP there. You get about 2.5 ATP for each molecule of NADH, and you get about 1.5 molecules of ATP per molecule of FADH2. So you get proportionally more. But we're not interested in you guys memorizing the numbers largely because how much ATP do you need to do anything, right? So what we want to know is, what you to know is the relative, I'm gonna get off camera, the relative amounts, right? So phosphocreatine, very fast, not much ATP, doesn't last very long. Anaerobic glycolysis or fast glycolysis, you have a little bit more ATP, lasts a little bit long, has a little bit bigger capacity. And then lastly, the oxidative phosphorylated pathway, a lot slower, a lot of ATP, lasts, basically if this stops this pathway, if you run out of fuel for this pathway, then you're done, you're dead. Because this is like the way you do it when you're at rest. What pathway actually recharges, for lack of a better word, phosphocreatine is this pathway.
So if you're doing something like leisurely walking, you would be using primarily this pathway, and technically you could be leisurely walking for many hours.
Technically, anything that you could technically probably do forever. And then also, it depends how trained you are and what your genetics are. You see, like marathon runners, who are running at a pace that I could not sustain for 200 meters. So they're in, mostly the oxidative phosphorylative pathway, but I'd be in the fast glycolytic pathway. So this, what pathway you use depends on not only intensity, but your training and your genetics, what you're going into it with, and that you can change a bit. And then, so then you get a ton out of this. And
so somebody who's really well trained, they could go out for a jog and they would be primarily using this pathway, while
if they're trained for endurance, for aerobic capacity.
Right. So, but somebody who maybe is not used to running at all, they would go out for perhaps a jog and they would be using
at the same pace. Yeah, they'd be using primarily like the glycolytic pathway producing a bunch of lactate. And so that's why, you have the lactate threshold, and anaerobic threshold, really is a better indicator of how trained you are, because that can move up and down depending on your training. And that is being shifted. So basically you're shifting from primarily an anaerobic or a fast glycolytic as a primary ATP production source to an oxidative phosphorylated pathway. And you can see how that if you can get this pathway going, you can, and you become more efficient, you can go for almost forever. But if you want to put power on something really, really fast, then you're kind of stuck with whatever pathway does that well. And you kind of shift where the lines are, for lack of a better word. Yeah, so I think so that's going to be where I'm going to leave this video series. I'm going to see how people feel. We can look at, how fat and carbohydrates and proteins feed into these energy systems, because ultimately this is where you get ATP, this is where you get your energy, and all the other pathways that we talk about in chapter 3 is feeding into this or storing carbohydrates, fats, and proteins to then feed into this.